Hello? Okay, make sure we're all in the right place. Is this everybody? No? Is there a few more people? Okay. Is this the course you're taking? TPG 4105? Is it early? Veldig tidlig I dag. Det riktig faget? 4105? Grunnkurs I petroleumsteknologi? Ja. Kommer det flere, eller? Det liksom 20 eller 60, eller? Ja, da bør vi snakke om de andre. Okay, I'm going to lecture in English, and you can ask all your questions in Norwegian, and I'll answer you in Norwegian. And my name's Curtis Whitson. I teach petroleum engineering, reservoir technique. And this is the first time I've been asked to participate in teaching this introductory grunnkurs. This is a module that's part of the so-called reservoir teknisk part of the petroleum technology discipline. Does anybody have a problem with understanding my English? I'll try to keep it slow, but as I mentioned, if you have any questions or dialogue that you want to have during the 2 hours we have today, then you're welcome to speak Norwegian, and I'll try to do the same. We're going to talk today about what I term initial fluids in place. That's kind of an appropriate title for the topics that I was asked to cover this morning, and then again we'll meet on Friday, right? Friday morning. Is it same time, 8 to 10? Okay. Do you all know the different disciplines in petroleum engineering? What they are? Or no. Okay, petroleum engineering consists of basically three main engineering disciplines. The one is drilling, boring, which you've been talking about with Paul Scala. Is that right? Okay. So apparently that's over with. I don't know, maybe you finished or maybe you didn't. The second is what we refer to as production engineering, produksjonsteknologi. And I won't be talking about anything within the field of production engineering. Production engineering, what it does is that it takes the production of the gas and oil and the water from the point it enters the well bore that we just finished drilling in boring, and it follows that production of those fluids through the production pipe, which we call tubing, to the surface, where it's processed into typically three different production phases: water, oil, and gas. And we typically make money on the oil and gas, and we lose money on the water. That's production engineering. Reservoir engineering, which is what we're going to start talking about this morning, is the field that looks at the physics of flow within the reservoir rock. Okay? So basically it's everything happening within the rock itself. Okay? Does anybody know what a petroleum, like a reservoir rock looks like? Have you seen, did they bring out some examples and show you? Or okay. Let's see. Did it look like this? This is a rock. Did any of the pieces look like this that they showed you? You guys, I'm going to have to start telling some political jokes or something. I mean, this is just very slow. It's not like I'm into doing comedy, but I mean, you're going to kill me. Okay? Does this look like the rock that they showed you? Yes or no? No. Okay. This piece of rock is called chalk, right? Krit. The largest, most important oil field development in Norway The first major giant oil field, do any of you know what that field is called? Ekofisk. Ekofisk produces and contains about 6 billion barrels, and at a price of about $60 to $70 per barrel, you can figure out the economics on it, about 6 billion barrels of oil inside of rock that looks just like this. It is chalk. It is white when you get rid of the oil. Okay? It is white. It is one of the most unique pieces of rock that you'll find anywhere in the world because it has close to 40 and maybe in excess of 40% of the volume that you see here is nothing. It is pore space. 40% up to 45%. Typically, the sandstone rocks that you're probably shown is anywhere from 10 to 25%. This stuff, if it's got 25% porosity, there's nothing that's going to flow through it. But if it goes from like 30 to 45%, then you'll actually get economically producing flow rates of gas and oil and sometimes water, which is important for Ekofisk because today we're injecting water in what is probably one of the world's most successful enhanced oil recovery projects anywhere. In the Ekofisk field, we're injecting hundreds of thousands of barrels of water into that field, into this chalk, and it's pushing the oil out. Okay? So this is just as important, or just as, and it looks just like this when you get it cleaned up. Chalk. Permeability is around anywhere from 0.1 millidarcy to 5 millidarcies. Does that tell you anything? Do you know about permeability yet? Okay, well, somebody else is going to teach you about that. That's not part of my deal. The permeability is the number that says how easily the gas and oil and water flow through the rock. Okay, and if it's a number like 1,000 or 10,000 millidarcies, that's like Troll, Statfjord, like it's like a bathtub. It's just like, you know, just flows through it. If you inject water, it sinks. If you inject gas, it floats. Okay, it's like there's almost no resistance. If you have 1 millidarcy, which is like probably what this is, then you have to work at getting the fluid flow to move. So you have to have big pressure gradients. You have to either push here and pull here, or maybe like Ekofisk, you've got 600 bar initial pressure. It's 7,000. It's more like I have to calculate. It's 7,000 psi, pounds per square inch. So it's like 450 bar, you know, initial pressure. And so you put a pressure at the well that you're producing from of 100 bar, and now you've got a driving potential of 350 bar. And with that driving potential, and in Ekofisk, it's a little bit special because the chalk has been broken up into pieces about the size of this table. So the flow doesn't have to flow only through the rock itself, but there are fractures or small sprekker between each of these table-sized blocks, or maybe sometimes it's the size of the room. So most of the actual flow is going through that network of fractures. Okay, but the rock itself, the permeability in this is about 1, and you don't get much flow through that unless you push hard. Okay? That's all we're going to talk about permeability here. But it's a very important factor. And we produce economic oil and gas rates around the world from rock that has permeabilities 1,000th of this, 0.001 millidarcy, to rocks like Grane, Troll, Statfjord that are a factor 1,000 to 10,000 larger than that. Okay? So there's this huge range of how easy or how difficult the flow moves through the rock. Okay, and we're going to talk today about reservoir engineering things. But it's kind of the boring stuff because we're going to talk about the static part of the reservoir. What is down there? What do we find down in the reservoir? Gas, oil, water. Okay, how much do we find? Things like that. That's what we're going to talk about. So we're going to talk about initial fluids, and the fluids we're talking about are gas, oil, and water. And in place means initially down in the reservoir. When we make that first drilling through the reservoir and we discover what's called a discovery and an exploration well, the discovery well finds the gas, oil, and or water. It'll always find water. There's always water in the reservoir. Okay? That's the only thing you know for sure. There will always be water filling the pores of the rock. Some water, a little water, a lot of water. And today we're going to talk about how much water. And what's not water is, come on, gas or oil. Okay, and that's what we want. Okay, so it's important to know kind of what's there. Now, we're going to look at a very simple equation to begin with this morning, and that equation is going to consist of a number of different topics. And people like myself who have nothing better to do, can't get a job in the industry, we sit around at the university and we write books and papers and stuff. And people write books about every little piece of this very simple equation we're going to look at. They'll spend their whole life writing a big, thick book like this. I spent 12 years writing this middle blue book and the white book, I don't know, you know. And it's just incredible. Okay, so there's lots of details we're not going to cover this morning in 2 hours. Okay, so I'm going to try to distill what I consider the most important things that you guys who are going to become what? Your physics students? What kind of students are you? Huh? Geological students. Huh? Okay, so you're like geology or only geology? Like what else? I don't know. I don't know. You know, I get my paycheck. I don't even know what faculty I'm part. Ecote, is that the one I work in? No. Okay. So what are the different departments? You got geology. What else? You know, a good teacher, if they don't know who they're teaching, then I mean, you know, I can just. What else? Huh? Production and product development. Okay. Anything else? Physics? Okay, so there are some. So there's kind of a hodgepodge, you know, a big group of different people. Okay, so I have to distill down what I think that any Joe Blow you can go home and tell your mom and dad about. If you want to know about petroleum, I took a course in petroleum engineering. Are you interested in reservoir, mom and dad? It's really interesting. You take a piece of chalk and you get them all excited. I'm going to try to teach you what are the most important issues. Okay, but just a little bit about each one. And if you want to really get enthused about something, there's a lot of physicists writing big books about reservoir. Go off and specialize. Okay, so we're going to talk about initial fluids in place. And what I thought I'd do is, actually before I get started, I thought that I would tell you where you can go on the internet and find some very interesting, useful, aesthetically nice-looking information. Because what I'm going to do is I'm going to scribble and scratch and draw pictures that are not very nice, okay, and very, very semi-quantitative. But I'm going to send you a couple of places where you can actually get very interesting, useful information about what we're going to talk about today. Okay? I'll spend about 5 or 10 minutes doing that. And we're lucky because somebody, the state government or somebody, there's something called Oljedirektoratet, and they have a fantastic, from my perspective, a fantastic homepage. It's fantastic because it is quantitative. Okay, in engineering, we want everything to be quantitative. I don't want to hear politicians mushy about you know, well, we think we're going to drill in the north, and we think there's a lot of oil in the Gulf of Mexico. That's political science talking. But in this website, they have lots of very specific information, geologic information, engineering information, production data information. Could you come up here just for a second? I'm going to send this book around. And if you get interested in the oil industry, and you probably should, this is a fantastic book. You can order it. It's free, I think, from the Oil Directorate. It's the facts book about the Norwegian oil and gas industry. It tells about every field, a little bit, a lot. And on this internet site here, I just go in and I'll show you how I got there. It's just www.npd, which is the English version. Maybe it goes with Oil Directorate as well. Let's try it. Full day. Nope. Okay. So we have to go for the English version, Norwegian Petroleum Directorate. You know, the Americans are going to take over. Okay, and we come here. Now, on this, we've got different stuff here. and there's just a lot of stuff I don't even know what's there. But we'll try to move towards the data-related information. This is is a very, very fine reservoir engineer in the oil directorate. He's been there forever. Is Leif Hindraker. Let's see here. I just did this a few minutes ago. We wanted to go to, here we go. Produkter og tjenester. Fakta, statistikk, geologisk, geofysisk data. And that's the most closely related thing to what we're talking about today. Okay, so we'll pop there. Has anybody ever used this site? It is very nice. Okay, and then you've got seismic data, seismic information. You've got kjerneprøver, pieces of core like that. Pictures after pictures after pictures with analysis. Other well data. Structure elements, geological, well tolkning, letemodell. It's just full of stuff that gives more detail about what we're talking about today. So let's just pop into one of these, just kjerneprøve. I got lots of nice pictures. Here you see there happens to actually be in English, an article in English, how to obtain pieces of rock like that. Core cuttings is, you all know what cuttings are because you had a drilling course, right? When they drill, they use this big metal with diamonds rotating, and it crushes the rock into small pieces. Those small pieces are brought to the surface in what? Water, slam? Yeah, mud. And in that mud are these little pieces. They have to go somewhere, right? They don't just disappear. That's what we call cuttings. And they're little miniature pieces of rock that the geologists and engineers look at to try to see what's there. It's the first picture you see of what's down there. So they've got cuttings, oil samples, geochemical standards. And this article probably is, I haven't read it myself, but it should give you a good introduction to a lot of the things we talk about today. Okay, so you can pop into there. Let's see if we can find some pictures of, I'd like to see some pictures of cores. I'm not sure where they are. On the brunndata. Well, okay. But yeah, I just had to get there. Let's see. Nederst til høyre? Down here? There we go. 2-4. These are some of the Ekofisk wells. I don't know if we've got any pictures of chalk there. Let's see here. You just want to pick a well? Anything you like? 10, 10, 5, 1. I don't know what it is. It's probably a dry hole. Let's see if we... And then down here it's got about the history of the well, operations, cuttings available, cores available. No core in this well. That was a bad choice. Pick one here. See if we got some cores. No cores. God, I tell you. Anyway, there's got to be some. I think this may be down in the Gullfox area. No cores. We got to have some cores in here somewhere. Wiesen, that's a Norsk Hydro operated field. There's some pictures. Okay, they're about this big around. Okay, they slice them in 2 or 3, and then the company gets some, and the partners get some, and the oil directorate gets some of the samples. Then they cut little holes, they cut little samples, and then they make measurements. Permeability, porosity, saturation, etc. So this is what they look like, and you can probably go in and yeah, you see, you got laminations. You see the geologic lamination. You got, I don't know what interesting stuff there is, but okay. So it's fantastic. They've got the production data from every field in Norway by month. So it's a lot of interesting information. So if you're really interested in what we're talking about, you can pop over to this website. Any questions about that website? Okay, it's very. It's free. I think you ask for you write a note to the book. You tell them you're a student and you're interested in the oil industry and you'd like a copy of that book, and they'll send it to you. They don't charge you, I think. And if you can't get one from them, we've got some upstairs. I'll steal one from one of the meeting rooms. I think you get it free. Okay, initial fluids in place. Well, I'm just going to draw a picture. There's two types of pictures. I'm going to draw a top view and a side view of maybe a typical reservoir. Okay, this is a top view. So this is an aerial XY kind of display. And the edge of the reservoir, basically, let's say we might out here, we might have, there's reservoir out here, but it's probably containing only water. And inside this area, we find gas, maybe some oil, and definitely some water inside there. Whereas outside, there's only water. Okay, this is a top view. And then if we look from the side, let's say that we cut through a slice of this along the side, something like that, A prime. It might look something like this, some structure, maybe and this is the geologic zone. There's typically more than one, but I'll just draw one. Let's make two just. And these two geologic zones that I'm drawing, I'm going to tell you that they're probably not communicating. So that there's some schiefer or shale between them. So there's no flow between them in geologic time. They're separated. And we've got this, basically this water contact somewhere around here. Might be the same on the other side over here, and it might not be the same, the depth of it. So now we're talking depth. I'll make it the same, that right there. And maybe the water contact in the lower is down here. And what is it we're talking about there? This is the water contact. So it's this rock, sandstone, carbonate, whatever it is, and it primarily contains water down here, water here, and all of the pores are 100% full of water, okay, probably. And above this line here, you start getting hydrocarbons in varying amounts. And up here at the top, maybe the water saturation is only 10 or 20%. So this is kind of a side view. We've got a water contact. It's a very important number. And so now what we've got is a three-dimensional shape of two reservoirs, right? Any questions? So we've got this. This is kind of like this is a high here. That's the accumulation of the light hydrocarbons. They accumulate. There's a shale on top of this top reservoir. This is, we're going to call this. I'm going to do something really cool here and make it bigger. Okay, and then we're going to say that this is reservoir 1. Let's make this reservoir 1 and reservoir 2. Okay. Now, this reservoir 1, for example, might contain primarily gas up here and oil down here, followed by water below that. Okay? It's got gas at the top, and then below it oil and water. The reservoir 2 doesn't have to contain any gas. It doesn't have to contain oil necessarily because they're separated. They're geologically separated. There might be different migration history into the two reservoirs. Okay. And, you know, from one reservoir to the next, it might look very similar to reservoir 1. It might look very different. So let's make the second reservoir only containing oil. That's what everybody likes is oil, so we'll give it just oil everywhere. In reservoir 2. So what you start seeing is that you've got this spatial distribution of bulk volume, which is given by the integration of the geologic structure. And we're mainly interested in the bulk volume that contains gas and oil, right? So we can integrate out this bulk volume. But then on top of that, we need to know how much water is in the gas part of the reservoir 1, how much water is in the oil part, how much water is in the reservoir 2, etc. Okay? So, and the variation of that water saturation may vary very likely with depth, for reasons we'll talk about after the break. But it could also vary, you know, aerially, spatially, in the XY direction, for other reasons. Maybe the permeability and porosity is lower in the northeast corner, so the water saturation would naturally be, what do you think, higher or lower? It would be higher. If it's a poor quality rock, it tends to have a higher initial water saturation. Again, for reasons we'll talk about after the break. Maybe the southwest area, it's a better permeability and porosity. So maybe it's got lower water saturation. So what we see is that we've got a kind of a quantitative problem to define the initial fluids in place, is that we've got variation of basically everything in 3 directions. Now, what are the everything? Well, the easiest way to think about everything is to take a simpler problem, or maybe we can just make a list. Maybe you guys are clever enough to just figure it out. If I want to calculate the cubic meters of gas, okay, the cubic meters of gas, that is your question. You won't get a grade on the exam until you give me the answer, okay? What is the volume of the gas? What are the things that you need to know from me to calculate that number? Okay? Let's just start making a list. What do we need to know? The porosity. But the porosity does you no good unless you know what? No? What does the porosity tell us? What is the definition of the porosity? They don't have red. It doesn't look like this, but it's the same stuff. If I ask you what is the pore volume of this piece of rock, and I tell you, oh, it's got a 40% porosity, is that going to help you give me the answer to the pore volume? No. What are you going to have to do to figure out the pore volume of this piece of chalk? It's got 40% porosity. I want the answer. You say, well, I can't. You have to tell me what are the dimensions, right? You need to know the bulk volume. So at the very top of the list is the bulk volume. And that's a simple integration of these 2 pictures. And luckily, they've got software that does this for you at the click of a button. You know, the geologists draw the maps, and the software goes in and draws all the pictures, and you push a button, and it does that integration of the bulk volume for you. And there's a couple of guys from this department. They left in the mid-'80s, just to tell you a story, who developed a piece of software from 1997 to 2002, and they sold it, and it's just doing for what we're doing, exactly what we're going to be doing today and tomorrow. They sold this piece of software, developed in 1997, 1998, and then marketed and developed until 2002 for $500 million crowns. These 5 guys, one's in France and one's in, he's Swedish, so he went back to Sweden. He's whittling wood. And there's a couple other guys using all the money to make more money, you know, for some reason 100 million crowns is not enough. And they wrote software to do this for us. It's called Petrel. And Schlumberger, the biggest service company in the world, they bought this from these group of Norwegian guys. One suite. Okay? 500 million crowns. So that the engineers and the geologists like you wouldn't have to sit and do it like we used to do it when I grew up. Okay? The bulk volume has to be integrated out. To know that, what is the gas, you have to know that contact, right? This contact here has to be known, and that's called the gas-oil contact. By the way, this is the water-oil contact. Those contacts are very important because they mark the point where you have gas, where you have oil, and where you have only water. So we need contacts. And those contacts, in fact, can vary as a function of x and y, but they don't usually, but they can. Okay, what else do we need to know? In the gas cap, I said that there will definitely be what else with the gas? What else with the gas is there? I said there's something that is in every pore in every reservoir. Water. Okay? The question is how much water? Is it 20% of the pore volume? Is it 10%? Is it 50%? Because the difference between 5% and 50% is a factor of 10. And that makes a difference, even to geologists. Okay? So we need to know water saturation, because that will vary throughout the entire reservoir. We need to know water saturation. And then I'm going to tell you that in some reservoirs, life is not as simple as this is gas and this is oil. Okay? Life becomes more complicated sometimes. As soon as you get kids, you find out. Anybody got kids here? Okay, yeah. Okay, you know, right? You thought life was simple and good, and then when you get kids, you know it's good, but it's not simple. Okay? And that's the reality of reservoirs. It's not, I mean, like Troll. That's a gas and an oil and water. It's very simple. 10 darcies or 10,000 millidarcies. It's a wonderful thing, Troll. But a lot of the other reservoirs are not like that. Statfjord and Ekofisk and on and on and on. You get very complicated. And whether it's a gas or oil, it's not so clear. So actually what you sometimes need, and maybe I'd say 20% of the reservoirs in the world, you need some indication of the molecular composition. Methane. You might have some nasty stuff, hydrogen sulfide, etc. All these different components. The world's largest gas reservoir is not Stockman. Stockman. Any Russians here? Anybody heard about Stockman? You know, Norsk Hydro and Statoil are like, you know, you don't even want to know what they're doing, trying to get their foot into owning part of this big gas field up in the Barents Sea. They keep writing it's the big. It's not the biggest. The biggest one is shared between a little country called Qatar or Qatar. Anybody heard of that? It's just a little itty-bitty extension of Saudi Arabia. Okay? It has the largest gas reservoir in the world. It is about 20 times the size of Troll. About 20 times the size of Troll. And then Iran has about half as much of that on their side of the field. There's this line, and this field extends over the boundary. And this morning on the TV program, they showed this rerun with the Russian submarine captain. Have you seen this, the comedy? With Rolf, Vesselin? You know, you guys are so young. It's depressing. Anyway, there was a Russian submarine that came around 1980. They found it in the Norwegian fjord, and it came up to the surface, and they brought it. And then this Rolf Vesselin made kind of a comedy thing. And he was saying, "Oh, we're just doing fishing here. We're just fishing, you know." And he says, and they say, "Well, you know, you can't fish." You know, this reporter's trying to get him. You know, you can't fish in Norway. You're from Russia. He says, "It's very difficult to see the boundary down below." You know, so in this Qatar-Iranian thing, there's a boundary that the gas doesn't know. So whoever sucks the hardest gets the gas from the other side. Okay, so you can imagine how it's being developed. It's like not an army, but you've got these platforms here and these platforms there, protecting their side of the boundary. Okay? In that field, there are 4 geologic horizons. And the H2S content, the hydrogen sulfide content, it's a very complicating factor. Because the design of these huge, it's probably the world's largest petrochemical development. LNG, gas to liquids conversion, all these things going on in this area. And this variation of H2S, and it varies areally by geologic layer. It's bizarre. We don't know why it varies. Ranging from like 0.5 mole percent to 5 mole percent. And that variation is one of the biggest economic factors in the entire field development. Okay? So sometimes you have to even know the molecular composition. And troll doesn't matter. It's the same composition in the gas everywhere. There's no difference. In the oil, it's the same. So it's, yes? It's on the process equipment. Yeah, they do gas to liquids conversion. They do natural gas, refrigeration, liquefying the natural gas. Any of the impurities, the amounts of them become very important in the design of the facilities. So if the facility has been designed for 1.5 maximum percent H2S, and then you find it, and then you start drilling wells and it's 2%, then you can't process that. It's just very expensive processing equipment. Okay, so we need bulk volume, porosity. Clearly this is given by the geometric XYZ. This can vary in all directions. This typically is only a function of the depth. I mean, it's kind of at what depth the contact. And the water saturation, again, X, Y, and Z. And the molecular composition is typically a function mainly of the depth, but it can also be varying in X and Y direction. These are the things we have to know to define, simply define, this is how much gas we have, this is how much oil we have. I don't think we've left anything out. Bulk volume, porosity, saturation, contacts. Of course, the saturation profile gives you the contacts, in a sense, right? And then molecular composition. Now, I'm going to make a comment before we take the break about gas and oil. There are 2 kinds of gas, in a way. Okay? There's the gas down in the reservoir, the top of reservoir 1. We call that gas. We have oil at the bottom of reservoir 1 and throughout reservoir 2. Okay? Those are called reservoir gas and reservoir oil. But in the same sentence, 2 engineers, petroleum engineers talking to each other, they can talk about, oh, this oil and that oil, and they're talking about 2 totally different things in the same sentence. Oh, this oil, da-da-da, and then that oil, da-da-da, 2 totally different things. Well, the thing is that if we take this reservoir gas, kind of going the wrong direction, but to the surface, through our production pipe, we bring it to the surface. We have this big process separator about the size of this room, not quite, but big. It'll separate that gas into two or three what we call products. And that will be gas oil, and again water. Okay. And these are all what we call surface, and sometimes we call them stock tank, but that doesn't really apply to gas. Pipeline gas, sales gas, stock tank oil, pipeline oil. These are products. We can put them in a cup. If I had a cup here, we could put them in a cup. Okay? And look at it, stick our finger into it. We can't do that with the oil or the gas in the reservoir. I mean, if we have it in this room, it's in a container at 600 bar, so we can't stick our finger into it. Okay? So we've got surface products, gas, oil, and water, and we've got reservoir gas. And again, if we separate out the reservoir oil at the surface conditions through various processing, we'll again get products. Now these products may look quite different than the products we get from the gas, but we'll still call them gas, oil, and water. Again, these are surface products. There's a couple of special names. This one is often, if you've got surface oil coming from reservoir oil, we often call that crude oil. Okay? It's got some other names too. And then we've got a special name that we call this surface oil coming from reservoir gas. We typically call that condensate. Condensate. Condensat. Okay? Råolja is the Norwegian equivalent of crude oil, råolja, and condensat. So, yeah, the this and that, I don't know, the Garn oil from, it's not Garn, I don't know the geologic formations. Yeah, the Tor Formation oil in the West Ekofisk field produced some really nice condensate, or some really nice sales oil or something. And in the same sentence, you get the term oil being used for two totally different things. The reservoir oil will produce both surface gas and surface oil. So the reservoir oil will produce both. Likewise, the reservoir gas will produce surface oil and surface gas. Okay? So we have this naming problem. So this becomes an important thing when we define fluids, because up here, what is a fluid? Before the break, you should say, Curtis, what fluids are we talking about? Are we talking about the oil and gas in the reservoir? You can talk about that. But what people really want to know, the vice presidents, the politicians, your manager, what they want to know are the sellable gas and oil volumes, right? They want to know the. So typically the fluids here are surface. Therefore, because we need surface fluids, we have to add one more item on the list here. That's not there yet. Isn't this a cool toy? I mean, it's just really cool. Okay, we need one more on the list, and that is the conversion, or the conversion from a reservoir volume to a surface volume. Okay, we need these conversion factors. And the reason is because the information up here will only tell us what's in the reservoir. What we need are conversion factors from reservoir volume, reservoir volumes, reservoir gas, and reservoir oil to surface volumes, SG and SO. Okay, we need some factors. And those factors, we call them, these conversion factors, they are called formation volume factors, FVF. And the engineering term, and even the geologist, the only petroleum engineering a geologist knows is this term. And it's called the B, it's capital B, defined as reservoir volume over a surface volume. That's the way they're defined. Sometimes they have the little b, which is defined as the surface volume over the reservoir volume. It's just the inverse of big B. These are the formation volume factors needed to convert reservoir gas or reservoir oil volume to surface volumes. And those can also be a function of depth sometimes, certainly if it's a gas and oil. Big difference in the numbers. And on a very seldom occasion, X and Y. But this is unusual. So we need these volume factors, B, also to be defined. Is it unclear? Is it like third grade school, or is it, yeah? And then after the break, we're going to talk about coming up with these numbers. We're going to talk about the uncertainty in the numbers and how we come up with them, what kind of measurements we need to make. Is it crystal unclear? Okay. So we'll take a 15-minute break. Okay, we'll get started, and we'll have a brief review of the definitions that are going to be used in calculating the initial fluids in place. We'll start with porosity. It's defined as the pore volume divided by the bulk volume. There are two types of porosity that one has. The one called primary, and then you have something called secondary. The primary is the main pore volume. Interconnected. Typically, it's typically 95 to 99.95% of the actual total porosity. So I'll just typically 95 to 99.95. And say to 100% of the total porosity. Secondary may or may not be connected to the primary, or it may be just totally isolated. May or may not be interconnected. Types of secondary porosity include vugs. These are just simply like small caverns or holes. Fractures, probably the most common. I'm not going to get into it. Obviously, the main thing is the primary porosity. The range of porosity is anywhere from maybe 2 to 45%. Maybe the common range would be 2 to 30%. And we already talked about the rocks that have this very high porosity, 35, 40, and 45. There are very few chalk reservoirs in the world. And those are really the only ones that reach those kind of high levels of porosity. Any questions about porosity? What I will say is a little bit about the pore sizes. They're typically ranging from about 0.1 to 100 micron diameters. And at the one extreme you've got chalk, and the other extreme you've got maybe a clean sand, clean, unconsolidated sandstone. By the way, I should have mentioned this in the beginning. I don't exactly know how I'm going to get the information to you. Do you use It's Learning? Okay. So I need to become a teacher on this course. Right now I'm not. But what I'll do is I'll try to make accessible to you, or I will make accessible to you, the video of what you're seeing here with the voice and a PDF file of what I'm writing. So you can just relax. I mean, you can always make notes. I mean, it helps some people to stay awake. It helps some people to learn. But you don't have to do it. You will be provided this information. So if you feel like I'm writing too much, you're not able to really follow what I'm saying, then don't write. If you do it and you find it helpful, then fine. The chalk pore size distribution is very unusual. It goes from about 0.1 to 1 microns. Very narrow. Very narrow distribution. Everything within just one order of magnitude of diameter. So it's a very narrow distribution. This is frequency. Whereas the sandstone looked more like this. Maybe a better quality sandstone looked like that. Okay. So that pretty much covers the porosity term. When it comes to measurement of porosity, there are different kinds of what we call electric logs. Did anybody talk to you about electric logging or logging? When they drill the well, usually before they cement the casing, he did talk about casing, right, in the drilling section. Before they put the casing and cement it, they run on a wire different tools that measure electrical resistivity, gamma ray, Sterling, all sorts of things. Okay? Did anyone talk about that? Okay. Well, they do that. And on the website of the NPD, you can see examples of it. Very nice. They show all the different measurements. Well, log measurements, there are typically two. There's the neutron and a kind of a density measurement. These two are the main log porosity devices. You have core samples, which are much more expensive. And you saw not all the wells have cores because they're very expensive. So you don't take cores in every well. Core data. And there's very much in correlation and mapping. So most of what you'll be doing is you'll be taking a few measurements here and a few measurements there, and you'll be doing some kind of mapping, two or three-dimensional mapping of the porosity distribution. That's not really measurement, but measurement estimation. Okay. Probably you can say that the uncertainty in this kind of data is plus minus half to 3 porosity percentage. Okay. So if it's 35% porosity, the 3% porosity uncertainty might be 10%. If it's a 6% porosity and your uncertainty is within 3%, then that's not good. Okay. So and the way this is usually determined is that where you have core data and you have a true porosity measurement, you try to check and see how well does that compare with the log measurement. So there might be correlations of the correction term. This, I think, is probably a reasonable. Now, when you get Ola Torstetter, he'll be teaching you about permeability and porosity and things like that. You can go back and say, well, Curtis said this, and then he'll say maybe the same thing. Maybe he'll say something different. If he says something different, he's probably right. Okay. But I think this is probably about right. So let's look at water saturation next. SW. We have different names for, we have so-called connate water saturation. That's basically the initial. So that initial can be low or high. You've got SWI, which is referred to as irreducible. Water saturation. What that means is that that water is stuck. Okay, you're just not going to be able to reduce the water saturation anymore by gravity forces or acceleration or displacement or anything. It's kind of irreducible. The definition of SW is the water volume divided by the pore volume. Okay, so it's a fraction of the pore volume containing water. Of course, likewise, you've got oil would be the oil volume divided by pore volume, and gas would be gas volume. Now, these oil and gas are reservoir oil and gas divided by pore volume. So the sum of saturations of the different phases is, of course, 1. Okay. All right, any questions? The typical range for irreducible water saturation, 5 to 50%. The normal range would be more like 10 to 30% would be the common. In general, you can't say this in general because chalk, for example, has an irreducible close to 10. Okay, but in general, the higher the permeability, the lower the irreducible. Okay, I mean it doesn't apply to chalk. There are many exceptions to that rule, but what you can say is that kind of a rule of thumb for sandstones, for example, would be that SWI and permeability, which we've been talking about, 0.1, 1, 10, 100, 1,000, etc. Typically, it'll have this kind of trend in general. It's not linear. I mean, I haven't told you. I mean, this is. I'm just giving you the general trend. Okay. Okay, so that's the definition of water saturation. And here, the sources of measurement and correlation would be, again, logs would be at the top of the list, electrical logs, core data. That's pretty much all you have. And in logs, it's the resistivity measurement. With additional correction, other logs that help correct and get the answer more accurate. It's mainly the resistivity. And core, this is, you could say, this is very difficult to know for sure that the water saturation hasn't changed when you take the core from down in the reservoir to the laboratory. Okay, so it's difficult to get very accurate connate water saturations and irreducible water saturations from core data. This is difficult for SWC, but we use basically centrifuge or what's called porous plate. And again, I think Torchette will probably talk about some of these things with you. These are two methods to come up with SWI. And these should be plus or minus, I don't know, maybe 3. Saturation percent on the irreducible. Okay, so that's water saturation. We've got porosity. What else was on our list here? Porosity, water saturation, composition. Actually, instead of molecular composition, we typically these conversion factors. Sometimes I'll make this as a comment. Instead of the molecular composition, we use, instead of knowing methane, ethane, propane, it's enough usually to know the surface gas volume to surface oil volume ratio. In other words, we take a reservoir fluid, we take it to the surface, it results in a surface gas and a surface oil. The ratio of those two volumes is what's called the gas-oil ratio. It's got the term R. and it is a surface gas to surface oil volume ratio. So for Ekofisk oil, by the way, Ekofisk was an oil field, that ratio is about 300 standard cubic meters of gas for every standard cubic meter of crude oil. Ratio about 300. For Troll, the oil in Troll, the ratio is maybe 30. Cubic meters of surface gas per cubic meter of surface oil. In Smørbukk South, Smørbukk Sør, just out here, which is an oil, but it's probably got a gas oil ratio of 600, 500, yeah, 600. So, anyway, that's often used instead of composition, and sometimes it's referred to as RS, which means they call it the solution gas oil ratio, because it's kind of like it's the original solution GOR. Okay, so now we're left with contacts. Let's look at contacts. We'll come back to the gas oil ratio and the oil formation volume factor, or the B. Okay, contacts. How do we determine these contacts here? The definition of a contact is where the pressure of the two phases you're looking at, let's say water, oil, is where you have equal phase pressures. For example, oil-water contact, we've got the pressure of the oil equal to the pressure of the water. Okay? For gas-oil contact, the pressure of the gas equal to the pressure of the oil. And there's only one depth where that's the case. And that's the depth that we call the contact. Let's introduce a definition. Of what we call capillary pressure. Okay? Has anybody lectured about that in this course? No? Okay. Now define capillary pressure. P, C, capital, these are small p's, by the way. The symbol for pressure is small p. You can't really see it's small here, but it's a lowercase liten p. Capillary pressure is big P. Okay, so I write it like that. I'm going to define that as traditionally it's the light phase pressure minus the heavier phase pressure. Light phase, heavy phase. Okay. So, for example, PG minus PO, or PO minus P water, they would be the capillary pressure of gas oil. and that would be the capillary pressure of oil water. Okay. All right. Or you might have gas, water directly in contact. Be the capillary pressure of gas, water. So another way to define the contact is that the capillary pressure is equal to 0. Right? Now I'm assuming that maybe Torstetter will get into the details of how you measure capillary pressure and physically what it means and on and on and on, because this is his part of the course, I think. What I'm going to talk about is the practical implication of capillary pressure on the initial fluids in place. Okay? And I'm going to try to give you a picture of what it physically means. Okay? So let's say that we've got this reservoir. And we drill a hole in it. A little bit out of scale. Okay. Well, in Oklahoma we have 1 meter, sometimes 1 meters thick. I'm from Oklahoma, so sometimes you have 1 meter thick, and you're very happy. Okay. So that size well bore to the thickness is maybe right sometimes. Okay. So we've got this well. We get rid of the rock in here. And let's say we don't put any casing, any of this pipe. We don't cement any pipe. We just let it sit there. Sometimes they have this kind of completion. It's called open hole completion. If the rock is a very strong rock, sometimes they don't need to put the cement in the pipe. So let's say we do that. And we just leave the well for a week or a month or a year, whatever, for some reason. And we come back, and what we find is the following. You know what I do on the weekends with my kids now. Okay? We got a water column. If I would have had this, see, my daughter's 21, I got a 17-year-old and a 10-year-old. If I would have had this device back then, I wouldn't have gotten so much trouble for working on the computer all the time. I could have just had them on my lap here and, coloring, and actually we were doing work, It was really kind of, but it wasn't that good. Okay. Okay. If we just left the well like this for long enough, this is the picture that you would see. If this reservoir, the well drilling through the reservoir, if it passes through both a gas-oil contact and a water-oil contact. Okay? Because at this point here, at this particular point here, the water pressure is equal to the oil pressure, right? And at this point, the gas pressure is equal to a different oil pressure, right? But they're equal. And if they weren't equal, they would be adjusting themselves. So, in fact, this is our gas-oil contact. And physically, if you could do an experiment in the field, this is how you would do it. Now, we don't do that, but that's how you would do it. And this is the water oil contact, or oil-water contact. However you want it. I like WOC because it could be Witson Oil Company. You know, maybe someday I'll be have $500 million or crowns or something. You know. Oil-water contact. Okay. That's what it would look like. Physically, it would look like that because those pressures being equal, this has reached a static equilibrium, right? There's a static equilibrium that's been reached here. Now, what I want you guys to do now, because, you know, I get paid to work, but you guys have to pay the government to come here, right? Okay? So you have to do work, too, for the government. Right? So I want you to draw how the water pressure, because we have water everywhere here. I want you to draw how the water pressure in the reservoir looks as a function of depth. Okay? And you can base it on, partly on this, but obviously you can't base it on, since there is no water in the well bore, there's no water in the well bore here, except at this point and below, you don't know what the water pressure is above, right? So you have to use your mind. So if we plot the water pressure, at least we can do it here. That's our water pressure. And then once you finish the water pressure plot versus depth all the way to the top of the reservoir, I want you to plot then the oil pressure versus depth, and then the gas pressure versus depth. Okay? Depth and pressure. This is our scale. Any suggestions? How do you think that blue curve should look? The water pressure in the reservoir above that contact. Should it change slope? What is the slope given by? Right? But what is telling us the slope of this curve? If you go out and you have a 10-meter swimming pool, a swimming pool, okay? At the surface of the swimming pool, it's 1 atmosphere, 1 bar, right? 1.01 bar. But 10 meters deep, where you bury the competition, the Röcke style. The density of the water, which is 1,000 kilograms per cubic meter for water, times what? G, the acceleration due to gravity, which is 10, 9.8 is 10. So for 10 meters, it's the density of water, 1,000 times G, which is 9.8, times 10 meters. That's the pressure, extra pressure from 1 bar down 10 meters. And how much pressure will that be? Yeah, it's 1 extra bar of pressure. Okay? It's, what is it? It's 1,000 times 10. That's 10,000 times 10 is 100,000 Pascal. And 100,000 Pascal is 1 bar. So you go from 1 bar to 2 bar at the bottom of the swimming pool. So this is basically given by the water density times G. That's the slope. And that continues the same because that's just the way it is. It goes like that. It's about 0.1 bar per meter. Okay? About 0.1 bar per meter. That's the slope. So now you're supposed to plot the pressure in the oil. And all we know is that the pressure in the oil starts right here. Right? Because that we know from the well. If we go with a pressure gauge in the well and measure the pressure, you'll see that it's equal to the water pressure at that depth. So we have this common starting point right there. But the slope of the oil pressure in the well bore is given by its density, right? Which is lighter than oil. So it's going to have a slope that goes something like this. And that slope is given by the density of the oil times G. That's the slope. And then the gas pressure starts equal to the oil pressure right here. Gas pressure and oil pressure are equal right there. But the gas density is even less. So it goes pretty much up like that. And its slope is given by gas density times G. And when they actually drill the well, before they put the casing in, what they do today in most wells around the world, certainly in the North Sea, is they actually go down at maybe 20 points or 50 points. And they set a tool against the rock, and they suck out a little bit of the fluid there, okay? And then they let the pressure build up. So they actually measure the pressure of the fluid that's flowing into the tool. So they see from the sample what kind of fluid it is, and they get its pressure. And Schlumberger is taking your money to do that, to pay these Norwegian guys to become millionaires, okay, by writing this clever software, okay, because Schlumberger charges a lot of money to do those measurements. So what they do in terms of measurements is that they actually go in and will make measurements. Now they won't be able to see this fluid. This fluid configuration is a fantasy configuration. Is if you shut the well in for a long, long time. Okay? It would take a long, long time, weeks or months or years, to come to that final equilibrium. They don't wait around for that. Okay? So instead, what they do is that they make measurements of, with these tools. They isolate a particular part of the formation at a given depth, and they measure the phase pressure at that depth. And what they'll actually see are data that follow and look like this. Maybe the top of the reservoir point there. Those measurements of pressure versus depth using an open hole kind of flow tool, they actually make these measurements. And then they look at the slopes, and they're able to determine that, yeah, there's a change in slope, and the intersection of that slope and that slope defines that contact. So they're actually able to make the measurements if the permeability is high enough. If you have low permeability, it's difficult to get accurate pressure measurements. But in the North Sea, for the most part, you get pretty accurate. These are what we call MDT, or formation open hole pressures. MDT is the Schlumberger name. So, yeah.
Is it possible to measure also the oil pressure, or would we get like a mixture, or like an addition of water pressure and oil pressure?
Yeah. Basically, the pressure you get, it's a mobility weighted average. Okay? And, I mean, this MDT, nobody's ever proven this, but this is, I think, right. If you were to, it's basically equal to the mobility gas, pressure gas, mobility oil, mobility water, pressure water. So if you happen to be in a zone producing quite a bit of water and oil, you'll get some pressure between the oil and water pressure. But usually you flow only one phase. Yeah. But usually it's only one phase. And that's why you get this fairly clear trend. By the way, this is mobility, which is permeability of the phase over the viscosity of the phase. So the phase mobility is its permeability divided by the viscosity. Okay. We're about out of time, so at least now we know how we, from a practical point of view, determine the contacts in a reservoir. Now, so the measurement of contacts, just to summarize, is either by the open hole pressure depth type data. But for less expensive wells, I mean, like in Oklahoma, you don't make these kind of measurements. They're too expensive. So you can also use electric logs. And here again, it's typically the resistivity. That tells you it's either hydrocarbon or water. Okay? And then gas versus oil. The gas can be determined by electric logs using the porosity estimated from the neutron log minus the porosity from the density log. Okay? You get a higher porosity from the density log because of the light gas. So you get this significant difference between the density and the neutron porosity estimate. So it's another way, and that will give you a pretty clear picture that this is a gas versus an oil. So those are the two methods to come up with the contacts. And I think we've made it about as far as we can today. On Friday, I'm supposed to continue on this same topic. We'll talk about capillary pressures and this balance between the capillary forces and the density forces, and we'll come back to this same topic. And then we'll get into the formation volume factors and the gas-oil ratios also. Okay. Any questions before we leave? Okay. All right. See you on Friday.